Uh, Hello everyone. My project is design of space-time codes for linear modulation over fading channels, and I did my project in National Tsinghua University, Taiwan. And my internal guide is Dr. B. Himadipti. And the main aim of my project is to design the space-time codes so that I will achieve maximum overall space-time diversity gain, as well as maintain the high spectral efficiency. And normally, why do we need space-time coding? Because the wireless channel suffers many various time impairments like multipath, fading, interference, and noise. So, to provide reliable high data rate communication for the wireless channel, we developed the coding schemes. And in my project, I considered fading as my main issue and designed my space-time encoder. And this is my block diagram. In this block diagram, my main aim is to design the space-time encoder so that whenever a message is sent to space-time encoder, this space-time encoder decides which message should be sent to which transmitter so that we'll have an efficient communication. And I'm going to design even a space-time decoder so that we'll have the complexity, less complexity. And I use the tools MATLAB package as well as C programming languages to design my space-time encoding. And a new space-time encoding scheme is given in my project. Normally, a proposed in this normally a space-time encoder is a single block, but in my proposed scheme, I have added a convolution encoder along with a spatial encoder, and as shown in the figure. And this is the figure, and the input of the spatial encoder is the following. And in this, I have considered my signaling time as TST, and the bandwidth efficiency I have given it as the following mathematical equation. And the output of the space-time encoder is a vector function which is denoted by this, and it can be written as and in order to have, normally in the previous proposed schemes, they considered a memoryless spatial encoder. To describe that, we give a relation known as matching inequality. In my project, I even considered a memory as 1. And in elementary design of space-time coding, I have to consider both the design of convolution encoder as well as elementary design of spatial encoder. In elementary design of convolution encoder, I considered my bandwidth efficiency, and in elementary design of spatial encoder, not only the coding rate of the convolution encoder, even the modulation of the spatial encoder also will affect this. And the final output of spatial encoder is in the matrix form, and it is written as the following matrix equation. And the linear modulation technique which I used in my project is M-array quadrature amplitude modulation. And in this quadrature amplitude modulation, I have considered my memory unit as 1, and the following bound limits I have considered, where LT is number of transmit antennas, and this is my input signal. In this, the above equation, this points to the amplitude of the signal and this points to the phase of the signal. And this 16 QAM gray coded signal space diagram is given as this. And in my project, I have considered the rank criterion so that we'll get the diversity advantage. If we consider any two ranks, if their two ranks are equal, then the full diversity can be guaranteed. And I have considered even the determinant criterion so that it will give the coding advantage. And my next main topic is matrix design for full rank. In this chapter, we present the basic principles to design 4 matrices, and then we introduce the division algebras, and then we embed these division algebras into the field. Finally, we construct the 4 matrices using both cyclotomic field extensions as well as 9 cyclotomic field extensions. And for whole construction, we assume multiplication identity as 1. and my MLSD beta-byte decoder is I have used in my project, and previously we used to have maximum likelihood detection that is used without memory, but in MLSD beta-byte decoder I am going to use as my memory value as 1, and for this MLSD beta-byte decoder we use optimum decision rule, and the following rule is optimum decision rule, and in this the S is known as estimated signal and R is known as the received signal. I am going to take the minimum value of this, and these are my simulation results. This is the performance comparison of space-time codes with coded scheme and uncoded scheme. The blue line represents the coded scheme, the red line represents the uncoded scheme, and the curves, performance curves are plotted as information error probability rate versus bit to noise rate. When we compare the simulation results, it is proven that the uncoded scheme is not much efficient as the coded scheme, and these are the following references which I have taken from my project. Thank you.